Welcome to an introduction to real analysis where we're going through section by section, continuing here with chapter 1, section 3, absolute value and bounded functions. What are we going to do? We're introducing the absolute value function. We're doing so with a rigorous definition, including proofs and basic properties, including the triangle inequality, proposition 1.3.2. This is a crucial tool we're going to use over and over in this course, so we're going to state and prove it. Now, some straightforward notation and definitions regarding functions being bounded are going to be introduced. It's not a big leap. We have notation and definitions for bounded sets. So, a concept we're going to encounter over and over is absolute value. A useful way to think of the absolute value is as the size of a real number, and the absolute value of the difference of two numbers is the distance between them. So we're going to begin with the formal definition. Here it is. Definition 1.3.0 formally defined. The absolute value of a real number, denoted with those two lines around it, no doubt familiar to everyone going through this course, is defined as if x is bigger than or equal to 0, the absolute value of x is x, whereas if x is negative, then the absolute value of x is negative x. So don't think of absolute value the way many students do initially as it makes a number positive. That is true, it's useful, but it's not a useful way to start constructing a proof. Okay, the formal definition of an absolute value of a real number is a piecewise function. There are two cases. If x is bigger than or equal to 0, then you may replace the absolute value of x with x. If x is less than 0, then you may replace the absolute value of x with -1 times x. So many proofs about absolute values boil down to two cases. Is the thing you're taking an absolute value of non-negative, or is the thing you're taking an absolute value of negative? So here is a proposition that holds for any real number x. First, the absolute value of x is always bigger than or equal to 0, with equality if and only if x itself was equal to 0. Second, the absolute value of negative x is always equal to the absolute value of x. Third, the absolute value of the product xy is the product of the absolute values of x and y. The absolute value of x squared is always equal to x squared. The absolute value of x is less than or equal to y if and only if x may be placed in between plus and minus y. And finally, x is in between the absolute value of x and negative the absolute value of x, and at least one of those is actually an equality. So let's go ahead and begin a proof of the first item. We've reminded ourselves the definition of the absolute value off on the right. We're going to proceed by cases on x as is typical. Now, item 1 specifically has x equals 0 as a special thing to examine, so we're going to do three cases. Often proofs with absolute value, the case of x being positive and x being equal to 0 may be lumped together because in the definition they are. But as I mentioned, item 1 has x equals 0 as a special scenario, so we're going to treat that differently. First, assume x is positive. So we're assuming x is positive. That's one of our three cases. When x is positive, the absolute value of x equals x. And what did we know about x? It was positive. So if x is positive, the absolute value of x is also positive. Okay, so we have achieved that the absolute value of x is bigger than or equal to 0 as desired. And because it was positive, it is in fact not equal. So we have addressed part of this claim as well. Next, let's do the special case of x equals 0. Well, if x equals 0, then the absolute value of x equals x, but what was x? It was 0, which means it is bigger than or equal to 0 and actually equal to 0. Finally, if x is negative, well, when x is negative, the absolute value of x by definition is minus x, but if x is less than 0, minus x is bigger than 0, meaning it's bigger than or equal to 0 and not equal. So altogether, we have established every claim in item 1. Moving on now with the proof of the second item. Again, we'll do three cases. If x equals 0, well then x and minus x are the same number, so the absolute value of the same number will of course be equal. Next, suppose x is positive. Well, if x is positive, the absolute value of x is simply x itself. In this particular case, if x is positive, then minus x is negative. How do you take the absolute value of a negative number? You multiply it by -1. So the absolute value of minus x is minus minus x, What's minus minus x? It's just x. What did we already establish? That x is the absolute value of x. So when x is positive, the absolute value of minus x equals the absolute value of x. What if x is negative? Well, we don't really have to do a separate case for this, because if x is negative, then minus x is positive. We've already established that for positive numbers, this holds. Meaning, the absolute value of minus x will be equal to the absolute value of minus minus x. But as we've already remarked, minus minus x is just x. So when x is negative, we again have this equality. So in all three cases, whether x was positive, negative, or 0, the absolute value of x, the absolute value of minus x, same thing. Moving on to the third item. We'll go by cases. If either one of x and y are equal to 0, or both of them are not 0. If both of them are not 0, maybe they're both positive, maybe they're both negative, or maybe one is positive and the other is negative. So first of all, if one of the two is 0, then the product is 0. But here, if the product xy is 0, then we already know its absolute value is 0. And if one of these is 0, then the absolute value of 0 is 0, and you get 0 equals 0 on both sides. No surprise. If both x and y are positive, then the product is certainly positive. Since xy is positive, the absolute value of xy is just itself, but since x was positive, it is equal to its absolute value, and since y is positive, it is equal to its absolute value. So when both x and y are positive, you get the equality that was claimed. What if both x and y are negative? Well then, the product xy must be positive. So the absolute value of xy is equal to xy, because xy as a product was a positive number. However, since x is negative and y is negative, the absolute value of x is equal to minus x, and the absolute value of y is equal to minus y. But now, negative x times negative y is the same thing as x times y. We link them all together, and we get the desired claim. Continuing, what if one of x and y is positive and the other one is negative? We're just going to assume that x is the positive one and y is the negative one. You can repeat the proof just by reversing the letters if you really want. This is what we mean by without loss of generality. The proof is the same whether x is positive and y is negative, or just switch them. Okay. This is a way of saying that the claim is symmetric. If you reverse the two variables, it doesn't actually change what goes on. So it doesn't matter which one you assume to be positive versus which one you assume to be negative. So one of x is positive and one of x and y is negative. So the product is negative, meaning the absolute value of the product is equal to -1 times that product. Now we assumed x was positive, so it is its own absolute value, and we assumed y is negative, so the absolute value of y is -1 times x, and then you just check that indeed these two things are equal. So if if x is positive and y is negative, you link these two as desired. If x was the -1, you would do the same proof. You would just move this minus sign here. No big deal. So we can move on to item 4. By the third item, we know that the absolute value of x times x is equal to the absolute value of x times the absolute value of x. So we can start off right here. Now, if x is bigger than or equal to 0, this absolute value is itself. So the absolute value of x squared is just absolute value of x, aka x times x, aka x squared. Now, if x is negative, then the absolute value of x is just -1 times x. So again, you would have the absolute value squared is the absolute value times the absolute value, but then these -1s would cancel each other out. You'd end up with x squared again. Altogether, the absolute value of x squared is always equal to x squared. Moving on to the fifth item. First, let's go ahead and assume that the absolute value of x is less than or equal to y. Okay, now we'll have to establish this chain of inequalities over here. There are two cases based on our original definition of absolute value. Either x is bigger than or equal to 0 or it is negative. If x is bigger than or equal to 0, the absolute value doesn't actually do anything. So what we've assumed is that x is less than or equal to y. Now, we have assumed x is bigger than or equal to 0. Therefore, y must be bigger than or equal to 0 as well. So negative y is less than or equal to 0. but 0 is less than or equal to x, so we chain them all together, and we get that negative y is less than or equal to x is less than or equal to y. So when x was bigger than or equal to 0, we got this. If, however, x is negative, since negative x is positive, we can go through all of the same arguments here, and we just get this. Okay, here negative x is our positive number that must be in between plus and minus y. So when x is negative, negative x is in between y and minus y. If I now multiply this whole chain of inequalities by minus 1, this becomes y bigger than or equal to x bigger than or equal to minus y, which is exactly what is claimed. Okay, so if we assume this left, we end up with that right. We need to assume that x is in between minus y and y. Now we'll try to derive that the absolute value of x is less than or equal to y. Again, two cases. First, if x is bigger than or equal to 0, absolute value is simply the identity function, meaning this is the absolute value of x, and it's less than or equal to y. That's all we needed to establish. What if x is negative? Then, starting from our assumption, multiply everything by minus 1, in which case you get y bigger than or equal to minus x, bigger than or equal to minus y. So multiplying this inequality by minus 1 and then flipping everything left to right to get the same symbols that we had before, you end up with this inequality. But if x is less than 0, then how do you compute the absolute value? It is simply minus x. So here is your absolute value of x, and it's less than or equal to y. So no matter what, we ended up with item 5. Now let's move on to the proof of item 6. First, if x is bigger than or equal to 0, then the absolute value of x is simply equal to x, meaning you get this inequality right here, and you actually get equality on the right. And since this is bigger than or equal to 0, as is x, multiplication by minus 1 flips the inequalities as desired. So you end up with what you wanted. Negative absolute value x less than or equal to 0, less than or equal to x, which is equal to the absolute value of x. That was under the assumption that x is bigger than or equal to 0. What if x is less than 0? Well, then the absolute value of x is simply minus x. So we really do the same thing. Okay, minus absolute value would be minus minus x, which is just x. X must be less than minus x because x was less than 0. So minus x is positive, which is bigger than x. But minus x is simply the absolute value. So you end up with an equality on the left and a strict inequality on the right. Okay, up here, the only way we could have had equality over here is if we had x equals 0. So you get at least one equality. The only way you can actually get two equalities is if x equals 0, and then you just have 0 less than or equal to 0 less than or equal to 0. Moving on to probably the most important result of this section, the triangle inequality. For all real numbers x and y, the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. Well, let's get proving. We're going to rely on proposition 1.3.1, so I've reminded us of what that content was. So part 6 gives us this and that. Okay, we can do it with x and we can do it with y, which means we can add them together to get the following. Negative quantity absolute value x plus absolute value y is less than or equal to x plus y is less than or equal to absolute value x plus absolute value y. What about part 5? Part 5 tells us the absolute value of a number is less than or equal to something if and only if it may be trapped in between that and that. So this parenthetical number, absolute value x, absolute value y, added together, I have this thing less than or equal to this number, but bigger than or equal to negative that number. So we have one number in between plus or minus the same thing. That is if and only if the absolute value of the middle is less than or equal to the thing on the right, which is exactly what the triangle inequality was asking us to establish. An immediate corollary of the triangle inequality is what's called the reverse triangle inequality, and also this right here, that the absolute value of x minus y is less than or equal to the absolute value of x plus the absolute value of y. We'll go ahead and prove these. So we've reminded ourselves both of the triangle inequality, because we are claiming this is a corollary of it, and proposition 1.3.1. So first, let's take a look at the reverse triangle inequality. Note that x is x minus y plus y. Okay, so apply the triangle inequality to that. The absolute value of x is equal to the absolute value of, well, this is just x, but now I have one number plus another. So I'm going to split it up according to the triangle inequality. The absolute value of one number plus a second less than or equal to absolute value first plus absolute value second. So one number plus another in absolute value less than or equal to absolute value of first plus absolute value of second. Now we just move some terms around. Okay, if I throw this on over to the left, we get absolute value of x minus absolute value of y less than or equal to this right here. That's awfully close to what we are trying to prove. We just need to be able to put an absolute value on the thing on the left here. Okay, we repeat the same argument. Instead of calling x equal to x minus y plus y, we repeat the same computation with y minus x plus x, and we end up with the absolute value of y minus x less than or equal to the absolute value of y minus x. But simple algebra, y minus x is -1 times x minus y. And from part 2 of prop 1.3.1, I can ignore that minus sign. So the absolute value of minus x minus y is the same thing as the absolute value of x minus y. So if I multiply this inequality by -1, notice that the absolute value of y minus the absolute value of x, when I multiply by -1, will become the absolute value of x minus the absolute value of y. And we'll end up with that less than or equal to absolute value x minus y, but bigger than or equal to, once I multiply by -1, negative the same thing. So whatever this is, it's in between this number and -1 times it. Well, if something is in between a number and -1 times it, that's if and only if the absolute value of the thing in the middle is less than or equal to the thing on the right. So the absolute value of this is less than or equal to that, which is exactly what the reverse triangle inequality is asking us to prove. So we've established the reverse triangle inequality, item 1. Let's move on to item 2. This is actually very simple. X minus y is simply x plus minus y. So the triangle inequality, we split that up. X minus y is x plus minus y. The absolute value of first plus second less than or equal to absolute value first plus absolute value second. So absolute value of x plus absolute value of minus y. And from item 2 here, the absolute value of minus y is just the absolute value of y. So altogether, we end up with this. We really establish item 2 as its own thing just to point out a pretty common error. The absolute value of x minus y doesn't get broken up as the absolute value of x minus the absolute value of y with the triangle inequality. Nope, with a plus. And this is a very common error because the triangle inequality has the absolute value of one thing plus another, and then you replace it with one absolute value plus another. People get in the habit of just saying, oh, the plus stayed a plus, therefore a minus will stay a minus. But the whole purpose of item 2 of corollary 1.3.3 was to show that's not quite true. The absolute value of x minus y is less than or equal to the absolute value of x plus the absolute value of y. As a nice little counterexample, suppose the absolute value of y was bigger than the absolute value of x. If this was larger than that, then this difference would in fact be negative, and you cannot have this absolute value be less than or equal to something negative. Another corollary, for any natural number, if you have a collection of numbers, so x0, x1 up to xn, if you add them all up and then take an absolute value, this is less than or equal to adding up all of the individual absolute values. How would we prove such a thing? Well, for n equals 0, there's not anything to prove. This is just a single number, and this is just a single number. So you, in fact, get equality. Now, for n equals 1, that's the triangle inequality. You have x sub 0 and x sub 1. Great. So we've already proved our base case of n equals 1. N equals 0 is hardly even a case worth considering. But the real base case of n equals 1, that's the triangle inequality. So moving on with an inductive proof, Let's assume for some n at least as large as 1, the claim as desired holds. Now we can use the triangle inequality and this assumption. If I want to take this sum out to index n plus 1, ignore this absolute value for the time being. The sum of all these numbers from index 0 through n plus 1 is the sum from 0 to n plus this last term manually added on. Now apply the triangle inequality. Consider this sum as a single number. The absolute value of first number plus second is less than or equal to absolute value of first plus absolute value of second. Our inductive hypothesis says that this sum can be replaced with this one, so less than or equal to that. But now we have a sum of absolute values going from index 0 to n, and then the next absolute value manually added on, so we can reincorporate it into the sum by having it end at index n plus 1. And we've ended up with the same formula we wanted, just extended to one index more. So we have proved this inductively. So here's an example. Can we find a real number m so that x squared minus 9x plus 1 is less than or equal to m for every real number x between minus 1 and 5? Now, from corollary 1.3.4, that x squared minus 9x plus 1 is just a sum of three terms. So I may say that the absolute value of x squared minus 9x plus 1 is less than or equal to the absolute value of x squared plus the absolute value of negative 9x, but I can ignore that minus sign, plus the absolute value of 1, which is simply 1. Well, this 9 can factor out. Okay, the absolute value of 9 times x is the absolute value of 9 times the absolute value of x, and the absolute value of 9 is simply 9. Also, we already know that the absolute value of x squared is the absolute value of x squared. So the absolute value of x squared minus 9x plus 1 is less than or equal to absolute value x squared plus 9 times absolute value x plus 1. Now note, this quantity is increasing if the absolute value of x gets bigger. If the absolute value of x gets bigger, this gets bigger, and this gets bigger, so the sum gets bigger. So it will be maximized when the absolute value of x is as large as possible. So in this example, between minus 1 and positive 5, the largest absolute value is at 5. Plugging a 5 in here gives a total of 71. So we can concretely say that the absolute value of x squared minus 9x plus 1 is definitely less than or equal to 71. Now, there are smaller numbers m that one could find to put here. That's not really the point. The bound of 71 is far from optimal, but we didn't actually ask for the smallest possible m so that the absolute value of x squared minus 9x plus 1 is less than or equal to m. Just find one such number, and here we have it. Notably, we didn't actually need any calculus here. Okay, next definition, 1.3.6, marginally different from how it appears in the text, although equivalent. Suppose f maps the set D to the real numbers and is a function. Then we say that f is bounded above or bounded below or simply bounded if the range of f is bounded above or below or bounded. So the terminology of calling a function bounded or bounded above or bounded below is just actually talking about the range of the function. So let's move on to this little lemma, 1.3.6a. This isn't in the text, but it will lead into that lemma. For a set A in the real numbers, define the absolute value of a set to be the set of all possible absolute values. Then the original set A is bounded, meaning above and below, if and only if the set of absolute values is bounded above. Essentially, to find if this set is bounded both above and below, you need only establish that this set is bounded above. So let's get to proving. First, let's assume that the set of absolute values is bounded above, meaning there's an upper bound, we'll call it capital M. The absolute value of A is less than or equal to capital M, and this holds for every element from the set capital A. Think back to Prop 1.3.1, item 5 in particular. If the absolute value of one number is less than or equal to another, you can place it in between plus or minus that, meaning A is in between plus or minus M. Since this holds for every element of A, we have found an upper bound, capital M, and a lower bound, negative capital M. I'm not claiming this is an infinite soup or anything like that, just an upper and a lower bound. Now we got to go the other way. Suppose that the set capital A has an upper and a lower bound. So let's call the lower bound M1, upper bound M2. Every element of the set is in between these two numbers. I'm going to replace M2 with something that might be bigger. I'm going to replace M1 with something that might be smaller. Specifically, from item 6 over here, m2 is less than or equal to its absolute value, possibly equal, and m1 is bigger than or equal to negative its absolute value, and again, possibly equal. So now I have a is in between these two values. I'm going to again replace this with something that might be bigger and this with something that might be smaller. I have a two-element set here. Absolute value m1, absolute value m2. Pick whichever one is bigger. The bigger of these two things is at least as large as one thing that was in the set. Similarly, take this number, negative absolute value m1 and negative absolute value m2. Pick whichever is smaller. That will be less than or equal to one of the numbers that was in the set. So now every element of capital A is in between these two values here. And going through this work was to use the following construction. This number on the right, the maximum of these two absolute values, just call it capital M for convenience. And recall back here, okay? Because this is a two-element set, the maximum is the supremum. So over here, I have the supremum of a two-element set. That's what I've called capital M. I'm going to multiply by a negative number. Specifically, I'm going to multiply by -1. So -1 times m, the maximum of this two-element set, is equal to the infimum of take every element of that set and multiply it by -1. But since this is a finite set, if I multiply everything by -1, I get another finite set, and an infimum is actually a min. So what we have here is that the minimum of the negatives is equal to -1 times the maximum of the positives. In other words, A is in between plus or minus M. Now I can go back and cite item 6 here. Sorry, not item 6, item 5. If A is in between plus or minus M, I conclude that the absolute value of A is less than or equal to M. In other words, the set of absolute values is bounded above, completing the proof of this little preliminary lemma 1.3.6a. And now we get to what I'm calling theorem 1.3.6b. In the text, this is just definition 1.3.6. A function from a set D to the reals is called bounded if and only if there is an m so that the set of absolute values of f of x is less than or equal to m for all x in the domain. So this is what I'm stating as a theorem. In the text, this is simply the definition of a bounded function. But recall, I've defined a function to be bounded if its range is bounded. So let's prove it. So these are all of the pieces that we're going to put together. Recall definition 1.3.6. A function is bounded if its range is bounded. Now the range is a set of numbers. So by definition 1.1.2, this set is bounded if it has an upper and a lower bound. By what we just proved in lemma 1.3.6a, the set of f of x is bounded if and only if the set of all absolute values is bounded above, which is exactly the other hypothesis of this theorem 1.3.6b, that the set of absolute values is bounded above. So just by putting these pieces together, we prove as a theorem what in the book is a definition. We just had a marginally different definition. Our 1.3.6 is just slightly different than the book's definition. So here's another definition not in the text. For a function with domain D mapping into the reals, we define the supremum and infimum of the function as the sup and inf of the range if they exist. Very straightforward, not a whole lot to say here. Now we move on to proposition 1.3.7. Suppose you have two functions f and g mapping the same domain D into the reals and they're both bounded. Also assume for all elements of the domain f of x is less than or equal to g of x. Then the supremum of f of x is less than or equal to the supremum of g of x, and the infimum of f of x is less than or equal to the infimum of g of x. Okay, the proof is not that complicated. We're only going to prove the first one about suprema. The statement about infima is totally analogous. We leave it as an exercise. Now, the trap that one can fall into is thinking that in the statement of the theorem, this f of x and this g of x, that these two x's are the same. They're not really. Okay, the x is ranging over the entire domain. So both sides of this statement have an x, but it's bound by different quantifiers. So what will actually be less confusing is just to put a y on the right, the supremum over y and d g of y, and an x on the left, to not fall into the trap of thinking that the f of x and the g of x are always acting on the same x. Okay, so let's prove this statement right here. So let's denote f of capital D as the set of values. Okay, now formally speaking, this isn't super great. F is a function whose domain is elements of D, and now we're just defining that you can plug the set D into F, but I think we'll all be okay with it, that F of a set is just the set of all values that F can take. Similarly, we'll define G of D in this way. Now suppose that B is an upper bound of this set right here. In other words, you have an upper bound on the set of values that G can take. So f of x is always less than or equal to g of x, but every value of g is less than or equal to b. In other words, every value of f is less than or equal to b. So b is an upper bound. Every upper bound of g is also an upper bound of f. So since b is an upper bound on the values that f can take, and the sup is the least upper bound, the sup of f must be less than or equal to b. And this holds for every upper bound of g. But the sup of g is an upper bound of g. So you simply take an upper bound of g of d and let b equal the sup of g. And you get the statement of that theorem. Now, there is something to be careful about there. In that proposition, we used the given that f of x is less than or equal to g of x for all x in the domain to conclude that the sup of f is less than or equal to the sup of g. It's tempting to think that you can prove something like the sup of f is less than or equal to the inf of g, but that's really not going to happen. For example, if f and g are simply equal to each other, then this statement right here certainly holds because they're equal, but there's no reason that the sup would be less than or equal to the inf if these were the same function. Okay, so if you wanted to prove something about the sup of f being less than or equal to the inf of g, you would need something much stronger, that every value of f is less than or equal to every value of g, where you're allowed to plug different things in here. With that given, you could conclude that statement. Let's go over what we did in this section. Now, the absolute value function is probably nothing new to us at this point. But to prove statements regarding the absolute value function, it's quite handy to have the formal definition, that piecewise function definition. So very often proofs involving absolute values boil down to a proof by cases. The triangle inequality is a very fundamental inequality. We will use it, conservatively speaking, 2,000 or 3,000 times in this course, so be quite familiar with it. Also, it's helpful to remember that a set or a function is called bounded if its absolute values are bounded. This simplifies a lot of proofs in the future. If you want to claim something as bounded, just throw an absolute value and show it's bounded above. It's worth pointing out, of course, sets of absolute values are always bounded below by 0.